start the talk. First of all, we're very happy to have Aayush from UCLA talking today about I/O from well-founded assumptions. Aayush is a PhD student at UCLA with Hamid Sahai, and he's going to tell us about this breakthrough from a couple months ago. Before I give the floor to Aayush, though, I'd like to thank all the people at TCS Plus behind the scene. So that's Anindya Day, Sumega Garg, Gautam Kamath, Ilya Rosenstein, Oded Regev, Salil Shram, Thomas Vedic, and Eric Weingarten. And also plug the next two talks, so next week and the week after. We're going to have Omar Montasser from TTIC to tell us about adversarial pack learning. And we will have Sharef Ben David from Waterloo to tell us about a new minimax theorem for randomized algorithms. Okay, that concludes the plug and acknowledgements part. Now, again, we're very happy to have Aayush tell us about his recent breakthrough, and feel free to ask questions. As mentioned, you can type them in the chat or just raise your hand and I will unmute you. Yeah, that's pretty much all. So without further ado, Aayush, please start.
Okay. Good morning, good evening, good afternoon, everyone, depending on your time zones. So first of all, thanks to the organizers for inviting me and organizing this talk. And thanks for everyone to be here. So today I'm going to talk about how to construct indistinguishability obfuscation from well-founded assumptions. And I want to thank my amazing collaborators, Rachel and Amit, for an awesome collaboratorship over the past 2 to 3 years, culminating into this work. And the format of this talk, as Clement has already said, is extremely easy. Just ask questions whenever you want. And I'm happy to answer questions during or even offline. So what is it that we are trying to do? What is this indistinguishability obfuscation? Well, as a concept, this notion of program obfuscation has been around even in 1970s, where the goal was to make programs unreverse engineerable. But really, it was formally and mathematically studied in the work first time in by Barak et al., where they defined this notion of indistinguishability obfuscation as follows. So they were looking for a polynomial time compiler called I/O. What it does is that it takes in your program pi and outputs an equivalent version of the same program. By that, I mean that it doesn't change the functionality at all. So it preserves the functionality, meaning that input-output behavior is the same. But what it does is that it adds a lot of meaningful security feature to it. So just the way to capture is that if you have two programs, pi and lambda, and let's say they have similar size and they compute the same function, meaning that they have the same input-output behavior, but otherwise the internal implementation is different. Then once you obfuscate them, you get two programs that are hard to tell apart. So which means that sometimes I/O is hiding implementation differences. And therefore, it's capturing the notion of making the programs unreverse engineerable. So that was kind of the definition. And as you can imagine, it has turned out to be surprisingly useful in context of cryptography. In fact, most of the cryptographic applications that I have seen over past many years, like past 7 or 8 years, they could just be constructed from assuming I/O and some minimal amount of crypto assumptions, such as only functions and some other standard assumptions. So it really has proven to be quite powerful in context of cryptography. But today I want to give an example of how the scope of indistinguishability obfuscation extends even beyond traditional cryptography and how it's applicable to a domain such as software engineering. So now in this example, let me just give you a concrete example to demonstrate this. Now imagine that you are a software developer, okay? And you design this really nice piece of code, which has a very nice user interface and really expressive UI. And then it has some of your trade secrets embedded inside the code. Now, what you would like to do is that you'd like to rent this piece of software out in exchange of money, like you want to treat it as a service to some clients in exchange of subscriptions. Now, since you want to do that and there is money involved, it's very desirable that your potential clients might want to try this out, this software out before they buy in. So therefore, you'd like to create a demo version, but turns out constructing demo versions is not a easy problem at all. Like, in fact, if you one naive way in which you can construct demo versions is that you have to go over this piece of code line by line. So what you can do is you can obviously go over this user interface and hopefully set some flags on and off. So that should not be a problem. You can easily cripple the user interface. But when it comes to the rest of the code, you really need to make sure that none of your secrets that you have worked on for so long are even accidentally leaked out. So, and no matter how hard you try, you can never be sure that the demo version doesn't reveal, the code of the demo version doesn't reveal these secrets. So that's the problem. And now, if you had, now I'm going to give you a solution if you had IO at your disposal. So if you had IO, what you could do, you can obfuscate a code where you just cripple this user interface and then keep the rest of your code unchanged. So just as it is. So hopefully crippling the user interface is an easy thing. So, and then you obfuscate it. And what IO security tells you is that this piece of obfuscated code is indistinguishable to an obfuscation of an ideal version of demo that you could have come up with. The demo version, which has a crippled user interface and doesn't have any embedded secrets, or the ideal possible whatever you could have come up with. And because of the security, what you can do is that you can simply release this obfuscated code and just be rest assured that your secrets are safe. So that's kind of demonstrating how you can handle this problem. But now, of course, I'm being oversimplistic here because I'm not trying to trivialize at all the problems in software engineering. In fact, this example won't even make sense if you have an amazingly fast and efficient obfuscation scheme. And by the way, we are far, far, far away from such an obfuscation scheme. Okay, so the point of me giving this example is that if one day you can come up with an amazingly fast and provably secure obfuscation scheme, that can be a game changer in many settings, even beyond cryptography and such as this. Okay, so now let me talk about, like, kind of give you some of the brief survey of what is known in terms of constructions for IO. So up until now, we have several dozens of constructions. I cannot even manage to write down, and it's a rich and beautiful body of literature. But unfortunately, all of these constructions up until our work typically suffer from at least one of the three problems. So in some cases, the security is heuristic. By that, I mean, the construction itself is assumed to be secure, and that it actually means that the assumption is pretty complex. In some of the other cases, typically people manage to really simplify the assumption to a simple looking assumption. However, at the end of the day, it's still a new conjecture which hasn't been looked at enough by cryptanalysts, and therefore the overall confidence is low because of that. And rest of the times, what happens is that there are cycles of attacks and fixes. So typically a construction is proposed, and then there are some attacks on that, and then those attacks are fixed. And that cycle goes on, and which further lowers our confidence. Okay, so I mean, this is really oversimplistic here, and then unfortunately, I cannot even do enough justice to this rich and beautiful body of literature. But my main point is that because of these kind of issues, there was a slight, you could say, pessimism in the community about general feasibility of IO. And so a major open question that remained was that, can you construct IO from well-founded or well-established cryptographic assumptions? And in this work, what we do, we construct indistinguishability obfuscation, relying on sub-exponential hardness of 4 well-established assumptions. So let me now tell you about those assumptions. The first assumption is the learning with error assumption with sub-exponential modulus-to-noise ratio. The second assumption is the learning parity with noise or LPN assumption over large fields CP with sublinear error rate. The third assumption is existence of Boolean PRGs in NC0 with the polynomial stretch. And the fourth assumption is the symmetric external Diffie-Hellman SXDH assumption over bilinear maps. I know it might sound to some of you who are not from crypto community that I'm just throwing some jargons right now. Do not worry, I'm going to talk about these assumptions in a bit more detail and tell you what exactly they are. But the point is that all these assumptions have been around for at least 10 years, if not 15. And prior to this, all the known IO constructions required specifically newly conjectured hardness assumptions introduced specifically for the context of building IO. Okay. I'd also like to state that our result should only be seen as a feasibility result. In fact, it's horrendously complex because it goes via lots and lots of bootstrapping steps, and the eventual construction is just too complex. And hopefully we're hoping that one day we have something which is implementable, and it's a major open problem right now. So at this point, does anyone have any questions? Okay, so in that case, I'll proceed. Now let me talk about these individual assumptions, kind of give you like a brief definition and what they are about. So the first assumption we are making is the learning with errors assumption, which was introduced in the work of Regev in 2005. Okay, so it's a hardness of decoding assumption. It has its roots in coding theory. What does this assumption say? It says that it talks about indistinguishability of two distributions. In the first distribution, I'm going to have n random coefficient vectors AI chosen from ZP to the K at random. Okay, so now ZP is a field, and for now and throughout this talk, I'm going to think of this prime being sub-exponential in the dimension K. So I'm going to sample n random coefficient vectors AI from ZP to the K, where n is some polynomial in K. So you're sampling n polynomial in the dimension random coefficient vectors from ZP to the K. And then I'm going to give you noisy linear equations. Okay, so n linear equations where the coefficients are exactly AI. So I'm going to sample a secret S from ZP to the K at random, take this inner product mod B, and then add some error EI, which is chosen from a bounded integer domain. And for concreteness, think of it as being sampled from discrete Gaussian distribution with parameter sigma. Okay, just for concreteness. So you have these noisy linear equations. And now the distinguishing version of LWE says that this looks computationally close to AI comma uniform. You could also ask for a search or a decoding version where the goal is to recover the secret S. And it turns out that under a variety of parameters, they are equivalent. So search is as hard as decision. So there's that. But also what's so nice is that LWE, turns out this LWE problem, which is an average case problem, is at least as hard as a worst case lattice problem, which is an approximation version of shortest vector problem, also known as gap SVP. So just to be clear, if you have parameter sigma K and P for the discrete Gaussian dimension and the modulus, then it lets you approximate, solving this problem lets you approximate shortest vector problem with approximation factor approximately Kp over sigma. Okay, and that was kind of established in several works. And for our work, just to be clear, we require an approximation factor of 2 to the K to the epsilon, where K is the dimension, epsilon is arbitrary small constant. So what it's saying, if shortest vector problem is hard to approximate within 2 to the K to the 0.00001, even that is enough for our work to imply IO. So that was the kind of concrete thing that I wanted to give you. And just so you know, that this is kind of a routine assumption that we make all the time in cryptography. The second assumption we are making is the learning parity with noise assumption, which was introduced in the work of IPS in 2009. Okay, but really in non-crypto settings, it's implicitly even They are much earlier, this assumption. Now, this learning parity with noise is also a hardness of decoding assumption. It also has a similar flavor as LWE. So it talks about indistinguishability of same kinds of distribution. So we have n random vectors AI chosen from ZP to the L. So I'm just, for concreteness, setting a different dimension, which is L, chosen over the same field ZP. I'm going to compute inner products AI and S, where S is chosen from random from ZP to the L. But now the noise is different. So in LWE, we had a bounded integer random noise. Now I'm going to choose a sparse noise. So with very high probability, it's going to be 0, but with probability L to the minus delta, where L is the dimension, and delta is some constant between 0 and 1. I'm going to choose the noise at random from entire ZP. Okay, so it's random with probability L to the minus delta over ZP. Okay, and I'm going to give n noisy linear equations like that. And again, the same thing. I want to say that this is indistinguishable to AI comma uniform. Now, this is the distinguishing version. Analogously, you can also define the decoding version or the search version, where the goal is to recover the secret from the first distribution. And turns out here too, there is under a wide variety of parameters, actually the same reduction that works for LWE will also work for LPN. So there is some notion of equivalence between these two problems. And when it comes to the hardness, turns out that although in cryptography it was only introduced in 2009, in coding theory we have studied random linear codes since 1950s, and until now we do not know of efficient decoding algorithms. And the best known attack actually takes 2 to the L to the 1 minus delta time. So just to give you a handle, delta is determines the probability of error. The probability of error is L to the minus delta. If delta is chosen to be close to 0, the probability of error is large, and therefore the problem becomes harder. When delta is close to 1, actually then the probability of error is like 1 by L. In that case, the problem becomes really easy. In fact, polynomial time broken. So what this is saying that it takes time 2 to the L to the 1 minus delta. So with smaller delta, it's almost close to exponential. But again, I want to emphasize that this attack, actually, this decoding algorithm with BKW, actually it also has this sample complexity, whereas we are working with only polynomial sample complexity. And under those regime, it's even worse, the best known decoders. Now, when it comes to the parameter we are using, we are actually using arbitrary small constant delta greater than 0. And just as a comparison, the public key encryption, which was constructed by Aleknovich and adapted by into this version by AAB work that requires delta equal to 0.5. We are working with delta just arbitrary constant greater than 0. So ours is arguably milder in that sense. And when it comes to applications, we have, I would not say that it is as used as some of the other assumptions we are making. Still, very recently, we have been seeing lots and lots of use of this assumption. In fact, you can already see in all my citations are pretty recent. So that's that. The third assumption we are making is existence of Boolean PRGs in NC0. Now, Boolean PRGs, as you all know, are length expanding objects, right? They take n bits, output m bits. So it's expanding where m is some polynomial in n, let's say n to the 1 plus constant. And we are looking for PRGs in NC0. That means that the PRG should be evaluated in constant depth circuits. Another way to say constant depth is that the number of input bits that each output depend on, that is a constant, and that is called as locality. I'll just refer informally sometimes. Locality is just the number of input bits that each output bit depends on. From security, I'm sure all of you are aware of this. Security just says that if you sample the input x from 0, 1 to the n at random, then g of x looks computationally close to a random string of length m. Okay, so that's pseudo-randomness. And this is also a very extensively studied object. So this was actually formally, this assumption came only in the work of ICAST 2008, but this assumption has been studied even since the work of Goldreich, which is 20 years. And by now we have a very nice characterization of like what are some of the good predicates and what are the attacks and trade-offs between all those things. So it's a solid assumption in my opinion. When it comes to stretch, we are actually needing a stretch of n to the 1 plus tau, where tau is arbitrary small constant. So an PRG in NC0 with a stretch of n to the 1.00001 is also enough for us. Whereas the best stretch that you can hope for is something like n to the omega of d, where d is the locality. So n to the some constant times d, where d is a constant locality, and you can increase d to get much larger stretch. So that's sure.
I have probably a silly question. So
Sure.
your assumption is the existence of PRGs against which class? Against
Polynomial time, no, actually sub-exponential times circuits.
Okay. Okay.
Yeah, like it's a cryptographic PRG. You're trying to fool all, at least polynomial time circuits, but also yeah, also like sub-exponential actually for I/O.
Okay. Thanks.
Yeah, just to be clear, most for those who are not in cryptographic community, all the assumptions are assumed to be secure against sub-exponential size adversary. By that, I mean, if lambda is the security parameter, they should be secure against circuits of size 2 to the lambda to the epsilon for a tiny epsilon. Okay, so now this is the fourth assumption, symmetric external Diffie-Hellman assumption, which was proposed by Ballard et al. In 2005, but really it was studied even before that. And I won't go into too much depth of what this assumption is because I'm not going to use it too much, but just roughly let me give you a brief thing. So it's indexed with a bilinear map. A bilinear map is an object, as a map, which takes a tuple having two group elements, one from source group G1, other from source group G2, and both are cyclic groups of order P, okay? Vp is a prime, and it outputs an element in the target group, which is also a cyclic group of order P. And don't have to worry too much about it, but it's typically instantiable using standard pairings over elliptic curves, like Weyl and Tate pairings. The assumption we are making is a really standard assumption that comes all the time in cryptography over bilinear maps, okay? The only takeaway that I want to keep from this slide is that bilinear maps allows you to do degree 2 computations on secrets over ZP for a large prime P. So what I'm saying is that using this bilinear map, you can encode field elements in, say, the exponents of the group, and then it lets you compute degree 2 multilinear polynomials over that. That's just the takeaway, okay? And if, yeah, so that's all I want to say. So lets you compute degree 2 multilinear polynomials over ZP. Okay, so now let me proceed with the rest of the technical framework. So this technical framework is, in fact, you can abstract it out, and it has been followed by this work, and in fact, several other works which eventually built to this work over the past few years, okay? Now these works typically have their own new cryptographic frameworks and everything, but at the end of the day, the crux of a matter is a special PRG. That's what I want to argue here. So typically the framework looks like as follows. There is object 1, which is functionality enhancing primitive. It lets you compute high degree computation. It's implemented using homomorphic encryption or randomized encoding, both of which are known to be from standard assumptions. Then there is another object which they use, which is a special purpose functional encryption, which is used for some enforcement purposes. I don't have to worry about it, but it's also implementable using standard assumptions, typically on bilinear maps. So these two are taken care of. The third novelty, which is like one of the main new ideas, is a special PRG. And I'm going to define this special pseudorandom generator later, but by special, I mean that it has some notion of low complexity. Now, once you have this special PRG, what they do, they combine these three things, Okay, and often this combination is like a lot of work, and a lot of new techniques and ideas go into this. This is most of the times the most complicated part of the paper. And sometimes it also introduces some heavy machinery such as security amplification. But yeah, this is really a beautiful part of the work, which I would have loved to go over it, but unfortunately I can't because of the time. They combine these things and create an object called sublinear functional encryption, and which by another beautiful line of work, it implies IO. Okay. Therefore, it's enough for us to focus on this object, special PRGs, which is the only part which is kind of from known, like from the non-standard part. So this is where the action is. So therefore, for the rest of this talk, I'm going to look at this entire line of work from the lens and viewpoint of a special PRGs, and in particular, how it evolved over the previous few years. And it's only in this evolution that actually there was a really nice feedback from the algorithms community in the sum of squares and convex optimization community, which gave us constant feedback about these PRGs. And we have to, and this helped us to refine our intuition slowly and helped us to be where we are right now. So I'm going to talk about some of these notions of special PRGs with an aim to twofold aim. I'm going to tell you this story. And then secondly, the more important thing is that I also want you to slowly build up towards the main solution. So let's do this. So now I said special PRGs, what are they? So the key takeaway from the previous slide was that in order to build IO from standard assumption, it just suffices to build special PRGs from standard assumptions. Now, informally speaking, very roughly speaking, special PRGs are PRGs which are implementable by bilinear maps. Again, I'm not specifying until the very end what it means. Unless I absolutely need it, I will not tell you what implementable by bilinear maps means. But roughly, it means that the seed will consist of the input of the PRG will consist of some field elements, and I should be able to compute the PRG using degree 2 polynomials, multilinear polynomials over that. That's just the rough idea, and I'm going to formally tell you later whenever I need it, not until then. And the main theorem that we are of our work is that there exists a special PRG from PRGs in NC0 and LPN assumptions. We are calling our special PRG as a structured seed PRG, which I will also denote as roughly as SPRG. So just from this theorem, this gives you IO from LPN PRGs in NC0 plus the other assumptions, LWE and SXDH. Okay, so this is the main theorem. PRGs in NC0 plus LPN implies special PRG. Okay, so now let me tell you more about special PRGs with the aim to tell you the history and also building up to our solution. So the first special PRG, which was called as a 2-block local PRG, was introduced by Lin and Tesaro in 2018, where they defined this special PRG to be a PRG with the following structure. So input is going to be n bits long, okay? This is like standard PRG, nothing different. But I'm going to mentally divide this input into blocks, where each block is of size log lambda. Think of lambda as a tiny polynomial in n to the epsilon, if you will. Okay, very tiny polynomial. So I'm going to divide it into blocks, okay? And then the output, which is going to be m bits, and just for a rough example, I've put n lambda square, but it doesn't have to be that. So there are m bits, where every bit, as the name suggests, is a function of two inputs from 2 blocks. So this has a block local structure, okay? Just to put it another way, mathematically, you can write each output bit is a function of input applied in 2 blocks, some function applied on inputs from 2 blocks. And this, which blocks they depend on, that can be arbitrarily chosen. Now, what's the point? Why did they define it? The main idea was that actually it can be implemented by bilinear maps. It can actually be written as a degree 2 multilinear polynomial. So let me tell you roughly why. So there's a mapping which takes your input from 0, 1 to the n, okay? And now I know that input has a blocks, right, of log lambda bits. Therefore, I can take every block and pre-compute all the monomials in that block. So there are 2 to the log lambda monomials. Okay, and I'm going to replace each block with all the monomials computed by that block. So therefore, n bits goes to n by log lambda times lambda bits. Okay, essentially, what I'm doing is just taking the block, computing all the monomials and replacing it with that. So under this expansion, if you look at the output, which is a function of inputs from 2 blocks, right? I can always write it as another multilinear polynomial over the reals on this new input, which is degree 2. Because I've already pre-computed all the monomials. Like, so the high degree thing that I needed to do is no longer existent. I can just use monomials. So that is precisely why it lets you evaluate using bilinear maps. And then they showed that this plus standard assumptions imply IO. But unfortunately, this was broken. Broken in the sense that there was an implausibility. Again, I'm not calling it impossibility because you don't rule out everything, but you rule out enough so that there are no known instantiations right now. So this was in work of BBKK18 and LV18. What they showed was this, the main thing that was detrimental was that it was implementable by degree 2. And this inequality known as the symmetric version of Grothendieck inequality proven by Charikar and Wirth via sum of squares paradigm. So what they showed, what Grothendieck inequality, symmetric Grothendieck inequality is that it lets you very efficiently in polynomial time approximate the maxima over the hypercube. So if you have any quadratic function g, any multilinear degree 2 function g over 0, 1 to the n prime to r to the reals, then what it lets you do, it lets you very efficiently approximate the maxima of this function within log n factors. So fix any degree 2 polynomial arbitrary or g from 0, 1 to the n prime to reals, you can find efficiently an x hat such that g of x hat is the maximum, at least the maximum divided by log n, maximum over the hypercube. So now you already observed that the PRG itself was the degree 2 multilinear polynomial, and now I have this. They observed that using these two things, you can already rule out most interesting parameters. And that was kind of the implausibility that was shown by these two works. So the key takeaway from this is that you want to avoid degree 2 PRGs, which are computable by degree 2 real polynomials over the Boolean hypercube. That's what you want to avoid because this Grothendieck inequality is detrimental to that. And that's a lesson that we learned, we incorporated. So then the next version of PRGs that was proposed was degree 2 integer PRGs. So we said, so this was in 3 concurrent work, one by myself with Prabhanjan and Amit, another by Lin and Matt, and then the third by Agarwal, where we realized that, let's not work with Boolean hypercube inputs. Let's work with integer vectors. So each input is going to be now from minus lambda comma lambda to the n. Lambda is some integer. And then I'm going to compute this PRG as an integer tuple, m integers. And each integer output integer is a degree 2 polynomial from this on this input. Okay, and the coefficients are chosen in some way. I don't want to get into all that, but it's also an integer. And we want some weak property of pseudorandomness. Again, that's also not important. But the key point is that we thought that this is nice. However, again, the same algorithm created problems. In fact, the same algorithm that's used in matrix sensing and matrix completion literature came to kill us. So this is an impossibility which we showed in work with Boaz, Sam Hopkins, Pravesh Kothari, and Amit, where we showed that the same algorithm, nuclear norm minimization, which is used in matrix completion, also rules out many candidates. So in particular, you can write it as a matrix completion problem. Remember, we are having degree 2 polynomials. So I can compute a matrix which has all monomials of degree 2, which is EE transpose, right? Now our goal is to recover this matrix E, given these equations of the form YI, which are the outputs, some matrix inner product with E. This matrix is computed by the coefficients of the polynomial, and you want to find out complete this matrix E from the observations. So yeah, so nuclear norm minimization will run some SDP, and what we showed that that if the number of samples are n times polylog n, then you already rule out most natural classes of polynomials. In fact, all the known proposed candidates that time were either broken theoretically or experimentally. It's still as an open problem. Can you construct something which escapes such attacks? Yeah, so the main takeaway from this was that you also want to avoid completely degree 2 computation over the reals. So now the point of that was to show that actually I told you that you want to compute a PRG, which is degree 2 over multilinear polynomial over a field. And now I'm telling you that you cannot compute degree 2 computation over the reals, and that's bad. So it might sound like a dead end because like you'll ask, I mean, how do we even come up with a PRG like this? So turns out that there was I mean, I would say a slick idea. And this was known as degree 2.5 integer PRGs, and they are in double quotes because there's actually a funny story behind this, and I'm going to tell you about that later. But in this, this was in my work with the Prabhanjan and Amit, and then follow-ups with Rachel Lynn and Christian Matt, where we showed that actually to build IO, it suffices to you can have a PRG which escapes all these problems. So let me tell you how it looks. So your input is going to be an integer vector from minus lambda comma lambda to the n. This is exactly like the degree 2 version, right? And your output, now, I mean, you want to avoid degree 2. So your output is will have this component. You'll have some polynomials evaluated at E, which is degree 3 and up. So it's good that it's more than degree 2, right? And that's what we would have liked to compute. But we showed that you can compute this along with a leakage. Okay, you have to pay a cost for computing high degree polynomials. And the cost comes at the with this, the cost is exactly this leakage on the input. So let me tell you what this leakage looks like. So your input was minus lambda comma lambda to the n. So it's n-dimensional integer vector. Your leakage is going to be n LW samples where the error is exactly the input. Okay, so you have n LW samples, AI, AIS plus EI. AI and S are chosen at random, okay? But there's an error, EI, which is exactly the input. So, yeah, so you are providing a PRG part, but you're also leaking out this. Now, a natural question that you'll ask is, why are we giving out this leakage? What's the point? The point is, if you just, for time being, just remove this leakage and just look at this degree 3 computation that we did, of course, it is impossible that you can compute it using bilinear maps. You can't. And because it's degree 3. What you can do and what we show in this work is that if I'm also leak this, somehow using this additional information, I'm able to compute these degree 3 polynomials using bilinear maps, and that was the main idea. That's what we showed in that work. Okay, so that was it. Like I hope this is clear, and if you have any questions, please please ask me right now. Okay, so that was about degree 2.5 PRGs. Now let me come back to the story. So the story is that it's called degree 2.5 integer PRGs because if there was no leakage, I would have called it degree 3 integer PRGs, right? Because I'm computing degree 3 polynomials. But there is leakage. So the somehow community itself decided that they want to call it degree 2.5. And that makes sense. Okay, so the takeaway from this slide was that this was nice. Why was it nice? Because if you look at the attacks that applied to 2-block local PRGs and degree 2 integer PRGs due to SDPs, they no longer apply. In fact, if you ignore the leakage, we can show that you can provably resist attacks of sub-exponential size in the form of SOS lower bounds, you can show that those kind of algorithms won't work as long as the number of outputs are bounded by n to the degree over 2 minus epsilon. And this is in an ongoing work with Boaz, Sam Hopkins, Pravesh, and Amit. And when it comes to using the leakage, so when it comes to using the leakage, unfortunately, the only way we know how to utilize those mod p leakages is by setting algebraic equations and solving what's called as Grosvenor basis algebraic systems. But turns out you can also show that they will also take sub-exponential time. You can do some computation and show that that'll take sub-exponential time as well. So this is really nice. Like all the known attacks, none of them apply. But still, it's unsatisfying. Why? Because there's a really unusual leakage on the PRG input, and we don't know how to handle it and how to even prove security. So that was where we were before this work. And now comes our main contribution, this SPRG. So what we do in this work, roughly, we also consider a degree 2.5 PRG, meaning that there will be a leakage. The outputs will be Boolean. However, this time around, we will be able to prove that this is secure. Okay, we'll be able to prove that this is secure using bilinear maps. No, sorry, using LPN and PRGs in NC0. That's the main contribution. So let me give you an overview of how our PRG looks. So input is going to be a Boolean vector, sigma from 0, 1 to the n. Then the desired output, ideally you would have liked to have compute PRG in NC0, G applied on sigma. That's the goal. But of course, you cannot compute it using bilinear maps because this is the degree D computation, whereas we want to compute degree 2 computation. Therefore, I'm going to have a leakage. The leakage will look like this. Now the leakage is really different from the previous case. We now have LPN leakage over sigma on sigma. So there'll be n LPN samples encrypting sigma I. So let me repeat how it looks. There'll be coefficient vectors, n of them AI at random. And then I'm going to compute AI and S. S is some secret, also at random. And then I'm going to choose a sparse error, EI, which is 0 with very high probability, but with probability L to the minus delta, the dimension to the power minus delta, it's non-zero and random. And then that gets added to the ith bit of the seed. So there are n LPN samples, n is the length of the input bit. So inputs, so that's how the leakage looks like. Now, why we are doing it, what's the key idea? The key idea is that the sparsity of error that helps us. First, it lets us compute the PRG output using a degree 2 polynomial. But also, what it lets you do is to prove security, because note that the errors are not involved in the PRG part. None of the LPN stuff, AI, AIS plus E, is in the PRG part. Therefore, it gives us enough independence in the second in the LPN leakage versus the PRG, so that we can argue security. Okay, and in fact, the proof is so trivial that I could have done it here, but I'll do it on the next slide just to show you how easy the proof is. So the main theorem is that we construct this. This is the SPRG construction. Modulo how it's implementable using bilinear maps, that I'll tell you later. But this is how it looks like. And in this work, we show that SPRG exists, assuming LPN and PRGs in NC0. Okay, so now let me talk about the simple proof. So you have AI, AIS plus EI plus sigma and G of sigma. This is the distribution. Now, by LPN, AI, you can switch it with AI and uniform plus sigma I. So remember, LPN says AIS plus EI and AI, that looks close to uniform. That's the LPN assumption. So I replaced it because none of it appears in the PRG part. So it's like completely kosher to do this. Now observe that uniform plus sigma is identically distributed to uniform. Okay, so I can replace it like that. And finally, there is no information about the sigma in the left-hand side. I can replace it with random from 0, 1 to the m. And that's it. That's the proof. It's right here. So yeah, the proof is really simple. Does anyone have any questions at this point? I'm happy to take them. Okay. So just that's the security proof. The only thing I have not told you right now, first of all, what does it mean to be implementable by bilinear maps? I've not told you how to implement this using bilinear maps. And that's what I'm going to do in the next part of the talk. So SPRG construction details. Now, I need to set up some definitions just so that things are, you have a more proper handle on things. So just for that reason, let me not define SPRG formally. So SPRGs are nothing, they are just Boolean PRGs, but we are with a structured seed. So the seed has the input has a structure, okay? So like any PRG, it has also similar algorithms. So first algorithm is the index sampling algorithm, which takes in two things: a security parameter, which determines the level of security that you want, and n is the length of the input. Okay, so that's what it takes, and it outputs an index. Then there is a seed sampling algorithm, which takes in this index and it outputs a seed. Now, that's where we are departing from a standard PRG notion, the fact that seed can be structured to have a public part of the seed, P, and a secret part of the seed, S, okay? And the size is n times poly lambda. N is like, as I've already told you, n is like the length, so therefore n times polynomial. Think of really n as some large polynomial in lambda. Okay, so the seed samp outputs P and S. P is the public part, S is the secret. And then evaluation takes in the seed formatted this way, and it outputs a length m string from 0, 1 to n, 0, 1 to the m. This is identical to a PRG. The output is Boolean. Now, looking ahead, I have already told you about the leakage, right? So you should keep in mind that your P, public part of the seed, will look like this. It will have the leakage, LPN leakages, basically, okay, encrypting this sigma. And then evaluation is what you want. It's a desired computation, G of sigma. This is just to give you a handle. Now it needs some additional properties. It has to be expanding. The length of the output needs to be much bigger than the length of the input, right? The second notion is the security, which is also a similar adaptation to a PRG. Given the index, given the public part of the seed, why should appear pseudorandom? That's the security notion, and it's fairly straightforward adaptation to a regular PRG. Now comes the thing that I've hidden so up until now. What does it even mean to be implementable by bilinear maps? Well, what you want is your output to be some constant degree polynomial, which is only degree 2 over S. So bilinear map, what it lets you do, it lets you compute degree 2 multilinear polynomial over the secrets, right, which are encoded. But what we realize is that P is public, right? So you can compute some constant degree polynomial, which is constant degree over the public part, but has to be degree 2 over the secret. You cannot allow for more than degree 2 over the secret part of the seed. Okay, as a polynomial, it's constant degree over P and S, such that with a restriction that it's degree 2 over the seed, secret part of the seed. Is that clear? Sounds good. So, so now, yeah, so the question is, how do you construct this SPRG? How do you make sure that it's implementable by bilinear maps? So this is the desiderata. This is what you want. You're going to put the index AI coefficient vectors in the index. In the public part of the seed, you're going to put these leakages, right? Where this now, I want to just remind you once and for all, these AIS plus EI are chosen from LPN. ZP to the L is the dimension, and EIs are but not L to the probability L to the minus delta. They're non-zero and random, otherwise they are zero. And seed is of length n and at random, and G is the PRG that we are computing. It's a degree D, constant degree D PRG. By degree, I mean it's a degree as really a multilinear polynomial. So constant degree D PRG with a stretch n to the 1 plus tau. Now what you want to do, you want to find this private seed, which lets you compute in degree 2, the computation that model I just told you, this G of sigma, while maintaining that the size of the seed is small, much smaller than the length of the output. That's the goal, right? And then what we realize that this LPN sparsity that we did, like the encoding using sparse errors elements, right? This encoding using LPN, it already helps. Okay, so as a first try, what I'm going to put, I'm going to pre-compute all. Remember, PRG is a degree D polynomial. I'm going to compute all the degree D by 2 monomials in S. Okay, and I'm going to put it in the private seed. Okay. And I'm going to make sure that the stretch and all works out by setting the dimension of the secret to be smaller, small, so that the number of monomials, like the information that I'm inputting in the secret part of the seed, is not too much, and in fact, much lesser than n. So I compute all the degree d by 2 up till degree by 2 d by 2 monomials and put it in the private part of the seed, and then I compute this. Okay. So I compute g of b minus as. So g is the PRG as a multilinear polynomial, and I'm computing this polynomial. Now look at this polynomial. It's degree d as a multilinear polynomial. Therefore, it's degree d over b, right? It's degree d over a, and it's degree d over s. Okay. Therefore, since b and a are public, they don't matter. The degree d is constant, so I'm allowed to compute constant degree over the public part. The only thing is the secret is degree d over s, but I have already computed degree d by 2 monomials and put it in the private part of the seed. Therefore, it's just degree 2 in the secret part of the seed. Okay, so therefore it's in the required evaluation complexity. Okay, but this is exactly equal to g of sigma I plus ei. Remember, b minus as is sigma I plus ei. You can see the equation I have defined in the public part of the seed. Bi is ais plus ei plus sigma. Therefore, b minus as is exactly equal to g of sigma plus e, right? And now observe that this PRG is a constant locality PRG. So every output bit depends on only constant number of input bits, right? And this error is really sparse. Okay, this error is every error is 0 with probability 1 minus 1 by L to the delta. It's 0 with a very high probability, 1 minus 1 by L to the delta. Therefore, this computation y prime is equal to the desired computation y, g of sigma. This probability is at least 1 minus 1 by L to the delta to the locality, meaning that all the input that it depends upon, those in those coordinates, the error is 0. That's the probability. And this by union bound comes out to be 1 minus O of L to the minus delta, right? And that's it. That means, what it means is that you're already almost there. You're already very approximately computing this PRG accurately. Like most of the coordinates are correct, only the L to the minus delta fractions are incorrect. That's what it means. So you can compute in the expectation. So I'm going to define set bad output bits as those where the output is not correct, meaning the desired computation is not equal to the computed computation. So, right? So I'm going to define this set, and I can show that the number of bad elements is less than m by L to the delta. This is by linearity of expectation. And then finally, I'll use Markov inequality to show that the probability that the size of the bad is lambda folds more than the expected value is less than 1 by lambda, right? And lambda is a large number, so it's only with tiny probability that I'll have too many errors, right? So my goal, therefore, is to just focus on correcting m lambda by L to the delta errors, and that's it. I'll only care about that. And yeah, you might ask that what will happen with small probability, I might have more errors. In that case, I'm just going to give up and let standard cryptographic techniques, security amplification, to take care of that case. So my focus for now is just to correct. So what's so nice is, given m output bits, I'm able to compute m minus m lambda by L to the delta error coordinates already. And it's only like a tiny fraction, m by L to the delta, which are not correct. So the goal is to just fix those. Okay.
So just
sure.
You asked me to tell you 10 minutes before, so it's roughly that time.
Sure. Thank you. Thank you. So that's that. Now what you want to do is that you want to just correct these these t errors is like t is equal to m lambda by L to the delta. So now I'm going to define this correction vector, which consists of the desired computation, what you want, g of sigma, minus the computation that you did, g of sigma plus ei. And I want to first observe that how does it look? Well, it turns out it is a really sparse vector because I already showed that g of sigma is g of sigma plus e with very large probability. So therefore, the number of non-zero entries in this is m lambda by L to the delta, right? Now I want to somehow use this fact in order to put something in the private part of the seed, which lets me compute this y prime as g of sigma plus e plus correction, right? Because obviously, when you compute something and add the correction, you get the desired output, right? So I need to put something in the private part of the seed, which is short and lets me compute this function. Now, obviously, I cannot put the correction vector here because the length of the correction vector itself is dimension m, and m is already too big. M is the length of the output of PRG. Therefore, I won't get any stretch. So I cannot put the correction vector itself. So what one might say, okay, I know the correction is sparse. Let me just put those coordinates which are bad, coordinates which are non-zero. Let me just put that. That's m lambda by L to the delta. Yeah, I could have done that, but now the problem is that in order to evaluate, I'll need to somehow reveal this bad set, either to the index or the public seed or something I'll have to do. But that's also a problem. I cannot reveal bad because that will tell me which of the LPN samples had errors. That will reveal me that, and therefore LPN security is lost. Right? So I'll have to do slightly more intelligent approach. I will have to compress it in a way that I cannot reveal the bad output bits. So I hope this goal is clear. So therefore, let us try to see our main trick. So we are going to show how to correct one error. Let's say the correction is one sparse. There is only one non-zero entry in the correction, and let's see how you can do it. We are going to use the fact that correction is sparse along with matrix factorization. So let's see. What I'm going to do, I'm going to make a grid of size root m cross root m, which has exactly m elements, right? Now I'm going to find a mapping which takes in the output bits, right? And maps it into the grid. Okay, so I'm going to find a mapping. Then I'm going to somehow use the correction and fill it inside the matrix using the bijection. So m of phi I is equal to correction I, right? I'm just fill it in. And now observe that since correction was sparse, there's only one non-zero entry there. There's only one non-zero entry here. So this matrix is also sparse. It is one sparse, and therefore it's a rank 1 matrix. And now I can factor this matrix as U and V, where U and V are of dimension root m cross 1. U and V transpose are in dimension root m cross 1. Okay, so they're root m sized. And again, I put U and V here, put the index phi in the index, put the bijection phi in the index, and then I'm going to compute y prime as the thing that I could compute plus U times V evaluated at phi of I. So remember, U times V computes this matrix of corrections, and phi I is the location at which the correction for ith entry sits. So I get the corrected output now. Okay, just using this. So this is good. And the stretch is also fine because the size of UV is proportional to root m, which is much less than m, right? So that's it. That's about correcting one error. And you can extend this idea to up till root m errors. Actually, I've written lambda errors, but actually you can even handle m to the 0.49 errors from this. But we have much more errors. We have, in fact, m lambda by L to the delta. So this doesn't work. But what we show is that a similar an extension of this idea will work, where what we'll do, instead of having just one bucket of root m size root m, I'm going to have t buckets. Okay, t is the number of errors we want to correct. I'm going to have t buckets, okay, of size L to the delta, meaning the dimension is root L to the delta times root L to the delta. Okay, so the total number of entries in all the matrices combined is m lambda. Okay, so I'm going to just put it in t, make t buckets myself. And then I'm going to say do the same thing. I'm going to sample random maps. This is a random assignment function which takes every index in 1 through m, and phi bucket will tell me which bucket this entry goes into, and phi index will tell me which index in that bucket does that PRG output go. Okay, so it's assigned to the corresponding entry in the bucket. So then these are chosen at random. This is for our calculation to work. Didn't have to be random in the previous case, but they have to be random here. Now, once you have these assignment functions, then it's really simple. I'm going to do the same thing. Take the correction vector, map it in these buckets by using this bijection. Not bijection, sorry, they are injection now. So they are maps. Yeah, map it in and do the same thing. First, you observe that since these maps are random, the number of entries is m lambda. Using some Chernoff style calculation, you can show that all of them are lambda sparse, up till lambda sparse. Every matrix is going to get at most lambda corrections. Because just think about it, the number of buckets are t many, and number of errors are also t. So an expectation, everyone should get one error. Whereas our maps are chosen at random, therefore by Chernoff bound, you can show that with probability at least 1 minus e to the power minus lambda, each of them is going to get at most get a lambda number of elements. Therefore, each of them have rank lambda. Therefore, you can factor each of them with ui vi transpose, where each of them are in ZP root L to the delta cross lambda. Okay. So now you have managed to factor and compress this information of correction into these buckets. And now you do the same thing. You're going to put this in random assignment in the index, put these factors in the private part of the seed, and compute a similar function. Y prime is g of sigma plus correction. Now for ith symbol, the correction sits in matrix bucket I. Okay, so you and that's exactly equal to u of phi bucket I times v of phi bucket I, and you are going to query it at index phi and I. So now this is a degree 2 function over the private part of the seed, right? And then it computes g of sigma plus error plus correction in I. That's what it computes. And it doesn't leak bad at all, like the set of bad entries. So therefore the security is fine. But when it comes to the stretch, we have to be slightly careful in the calculation. So the size of the public part of the seed is already small. The size of the secret is exactly roughly the size of the matrices ui and vi. So there are capital T matrices, right? M lambda square by L to M lambda by L to the delta matrices, each of dimension L to the delta over 2 times lambda. Therefore, if you compute this entire size, this comes out to be M lambda square divided by L to the delta over 2. And now note that since L is much bigger than lambda, therefore you are still winning. This is much lesser than M. And that's exactly what the saving we get. And this saving turns out to be enough to get us to IO. And that's like the main idea. So does anyone have any questions at this point? Sounds good. Okay, so yeah, the security is clear. You already get something which is 1 by lambda secure, 1 minus 1 by lambda secure, because you're losing in the probability when the errors are too many. And then you use standard tricks, amplification to argue security, which I don't want to go into all that. Therefore, just let me leave you on the note of some open problems. So my main open problem is, can you construct provably secure, post-quantum secure indistinguishability obfuscation from well-founded assumptions? And when it comes to our work, you need to, if you can remove the reliance on SXDH, then that will already give you a plausible post-quantum scheme. But unfortunately, it's not clear how to do that. Our techniques are pretty tailor-made to bilinear maps, because we are building these PRGs which are implementable by bilinear maps. So it's not clear how this will work out. Another interesting new direction to address these kind of questions is coming up. And what they do is that they construct obfuscation from new circular security definitions on fully homomorphic encryption. So if you have a fully homomorphic encryption satisfying this new circular security definitions that these guys proposed, then that leads you to IO. And we hope that one day this also leads to something which constructs post-quantum secure IO from well-founded assumptions. But as of now, these assumptions are new and they're yet to be cryptanalyzed. So, but still we are quite hopeful that that happens. When it comes to the another one of the main question is the efficiency question. In fact, that's perhaps one of the most important questions. Can you construct efficient indistinguishability obfuscator from a well-founded or even non-well-founded, but like simple looking assumptions? So that's a really interesting open question that remains. Another question that I'm interested in is, can you construct even other approaches to yield IO from well-founded assumptions? And it's like it will be very surprising if ours is the only approach. There's no reason to think about that, but it's a really interesting question, and hopefully we'll see some other approaches also. So I'd like to conclude at that and leave the floor open for questions if you have.
Thank you for the talk. Yeah, so if anybody has a question, I think I allowed everybody to unmute themselves, should they want to, but
oh,
yeah,
I
thanks for the
saw
talk.
that there's some chat. None of them
Yeah,
get, oh, I see.
some people had to go, but they thank you for the talk. Yeah, and there was one question that you actually addressed during the talk as well. I had a very dumb question about one of the last things you said, which is,
sure.
So you mentioned that there's a new line, which is how to build IO from fully homomorphic encryption. Isn't there also like a line of work that says from IO you can build fully homomorphic encryption?
Yeah. So if you assume IO and randomized encryption, sorry, fully randomizable encryption, re-randomizable encryption scheme, which is typically instantiable from number theoretic assumptions, then you can construct fully homomorphic encryption. So this was a work in 2015. I think it was CLTV, Canetti, Len. I'm not sure of all the authors. So, but there was a work in 2015 that constructed homomorphic encryption from IO and some other standard assumptions.
So does that mean that the two are on some level kind of equivalent, or there's some fine print?
No, so this line of work that I was mentioning builds IO from specific assumptions on. So they're significantly simpler than previous assumptions, but they build it from specific assumption on specific homomorphic encryption. So you have a homomorphic encryption of GSW.
Okay.
They have a specific circular security style definition, which leads to that. So I'm not sure if it's equivalent at all.
Okay,
yeah, and like they're new assumptions still. So they're simpler, but they're still new.
Yeah. Okay, thank you. So yeah, if anybody has a question, they can unmute themselves.
And feel free to even reach out offline if you have any questions later. That's also fine.